Okay, we'll start now. So, is the video quality clear, or is it blurring or something? Can you just reply in chat once? All right. So, let's continue where we left yesterday. So, just once again. Yeah, so today let us first consider a comparison between the sodium, let's say, and silicon. So as we all know, this density can be written as rho gram per centimeter cube. So 1 centimeter cube obviously rho grams, and if m is the molar mass, so this is what we were discussing yesterday. So if m is the molar mass, that means number of moles will be rho by m, and 1 mole means 6 into 10 raised to 3 atoms. So this will be the total number of atoms in silicon. Alright. So number of atoms in silicon per centimeter cube will be around this, which is nearly 5 into 10 raised to 22. Now, yesterday we were discussing that some of the electrons, they are able to jump from valence band to conduction band, and so they are able to conduct electricity. Now what is the meaning of that some electrons? How many precisely? So that is called Ni, which is called intrinsic carrier concentration. What is intrinsic carrier concentration? Once again, it is the number of electrons per centimeter cube of silicon that have jumped from valence band to conduction band and therefore able to conduct electricity. Now that comes out to be roughly equal to 10 raised to 10 per centimeter cube. So let's compare this. The number of atoms which are there in 1 centimeter cube, which is of the order of 10 raised to 22, and number of electrons per centimeter cube which have jumped is only 10 raised to 10. That means out of 10 raised to 22 atoms, only in 10 raised to 10 atoms electrons have jumped. That means maybe 1 out of 1 million atoms, only 1 electron. So that is very less. That explains actually the low conductivity of silicon, because only 1 out of 10 raised to 12 1 10 raised to 12. Why 10 raised to 12? Because 10 raised to 22 atoms, 10 raised to 10 electrons. So 10 raised to 12 atoms, 1 electron. Okay, but what about sodium? Now the density of sodium, rho, is around 0.968 gram per meter cube, whereas its molar mass is 23. So if you do the same thing, it comes out to be around 2.5 into 10 raised to 22 atoms per centimeter cube. Now Sodium is highly conducting. Why? Because each atom will furnish one valence electron for conduction, because it's a conductor. So one atom, one electron. So how many electrons are available in 1 centimeter cube which can conduct electricity? This 2.5 into 10 raised to 22. So one atom, one electron in case of sodium, and one electron out of 10 raised to 12 atoms in case of silicon. So what we do to enhance the conductivity of silicon? So what we do is something called mixing impurities, which is called doping. So what is doping? Doping is adding of impurities. So impurities are actually of two types. So type 1 is which are called pentavalent impurities. So here I have written this pentavalent impurities. These pentavalent impurities have 5 electrons in their last orbit, and these are also called the n-type impurities. The another name for them is the donor impurities. Why they are called donor impurities? Well, what happens is when we mix these impurities, they dislocate some of the silicon atoms. So if this is, let's say, the silicon mesh 2D representation, one silicon atom is dislocated, and in its place a phosphorus atom has come. Phosphorus is pentavalent, 5 electrons in large shell. Okay, so 4 of the electrons of this phosphorus, they are able to combine with make a covalent bond with the silicon atom. But what about the last one? This is additional, the 5th electron. What happens to this 5th electron? The thing is that 5th electron is loosely attached to the phosphorus. Why? Well, what happens is that if you see here, where is it? Sorry for this. Okay, it's not here now. Anyways. Yeah. So there is a professor in IIT Madras. His name is Mr. Kalmakar. So he was explaining that this phosphorus atom is there in the silicon substrate. So it's like in a dielectric. Now dielectric constant of silicon is roughly around 12. So what happens is this force, Coulombic force in a dielectric medium, this force becomes 1 by k times, where k is called the dielectric constant of the material. So silicon being of dielectric constant of 12, so if we take this phosphorus nucleus and this last electron, the 5th electron in the valence shell, the attraction between them is decreased to 1 by 12 times, because we can say that that phosphorus atom is present in the material, which is silicon. So because of this, this last atom is loosely attached. And what is observed is that if we draw the energy level of this last electron, so we know that this is like 1s, then 2s and 2p, and this 2s and 2p. So this is for silicon, and this is the valence band, and this is the conduction band. So valence band and conduction band here, the energy is found to be somewhere here. This is the energy of 5th electron of phosphorus, and this gap is found to be roughly around 0.045 electron volt, which is very less as compared to the actual energy gap, which is 1.1 electron volt. So this 0.045 of electron volt energy is very much available to this 5th electron of phosphorus. So what happens is that this 5th electron of phosphorus jumps into the conduction band. So what does it mean actually? This electron here, the last one, this is actually not attached to the phosphorus nucleus because it has gone into the conduction band. In fact, this happens with all the donor impurity atoms or all the phosphorus atoms. The 5th electron of them will go somewhere into the conduction band, and we say that this electron is lost, so it has become a positively charged. And we say that the phosphorus atom is ionized because of the electron loss. And so we assume this 100% ionization of the donor impurities. Now, generally, for example, if we take this electron of silicon, if it will go somewhere here into the conduction band, then a hole will be created here, isn't it? But that's not the case with the phosphorus. So when this electron has jumped into the conduction band, there is no hole created because it's already 4 electrons were paired up, making covalent bonds. So because of extra electron, a hole is not generated, which means the electron number are increased but the hole number is not changed. And so the number of electrons will become much greater than the number of holes. And that's why we say that most of the conduction is done by the electrons because they are majority in number, and less conduction is done by holes. So we say that the majority charge carriers are yeah. So as I was explaining this 100% ionization of impurity ions, and because of each electron going into the conduction band, no hole is generated, and the number of electrons becomes much larger, whereas number of holes is not changed. But that's not the case actually. Actually, the number of holes decreases. Why the number of holes decreases? Let's say in the silicon there were around 100 holes previously. And how many electrons were there before adding the impurity? Obviously, the number of holes is equal to number of electrons. But once we have added this pentavalent phosphorus atoms, more and more electrons are there. Now these electrons in this conduction band, they are roaming all around the crystal lattice. And what they do is, sometimes they find the holes. For example, this electron which has been generated here, it may be moving all through the silicon atom and maybe all through the silicon crystal, and maybe it may come to this silicon hole here, and it may come into the hole and fit in. And once this electron fits into this hole, we say that a recombination has taken place. So what will happen is, the electron hole pair will get destroyed, because now the hole is lost. Once the electron comes and fits in, hole is lost and the free electron is also lost. Now, as compared to previous case, that means before adding the impurity, as compared to this, after adding impurity, lots and lots of free electrons are created because of the 5th electron going into the conduction band. So huge number of electrons are available. So the probability that those huge number of electrons will find those holes and combine with them is large. So what happens is, because of the large number of electrons present, some of those electrons are able to go into those holes and fit in there, and thus the number of holes is destroyed. Alright. Now, theoretically, some semiconductor theory is there. With the help of the theory, it has been established that the number of electrons per unit volume, Ne, and number of holes per unit volume, which is NH, the product of these two still remains Ni square. Before adding the impurity, one second. Before adding the impurity, Ne was equal to NH, because each electron going into the conduction band will result in exactly one hole. So one electron goes, one hole is created. So Ne was equal to NH in pure silicon, which is called intrinsic type. And we know that that is roughly of the order of 10⁻10 per centimeter cube. And that we call as Ni, the intrinsic carrier concentration. Whereas the atomic concentration is around 10⁻22 per centimeter cube. That is the atomic concentration. Now after adding donor impurities, because they have donated their electron, lots and lots of free electrons are available. So this has increased, this has decreased, but it has been established through some theory that their product still remains what it was before adding impurities. And before adding impurities, both of them were equal to Ni, so their product was Ni square. Even now, after adding impurities, their product still remains Ni square. One has increased Ne and other has decreased Nh. Why the holes have decreased once again? Because the electrons have combined with some of the holes. Now, there is an assumption which is that the donor impurity concentration, which is called Nd, Nd is the donor impurity concentration. This donor impurity concentration is the number of donor atoms per centimeter cube. For example, in 1 centimeter cube of silicon, there are around 10 raised to 22 atoms. 1 centimeter cube, 10 raised to 22 atoms of silicon. Now the donor impurity is kept quite low as compared to the silicon concentration. Donor concentration is kept very low. So obviously if we put too much of impurity, then instead of silicon it will become actually phosphorus, isn't it? So we don't want to convert the silicon into phosphorus, we want the silicon to be remaining silicon, but some impurities here. Yeah. So for example, the donor impurity concentration is somewhere around 10 raised to 16 per centimeter cube. So Nd by atomic concentration of silicon will be 1 by 10 raised to 6, which means out of 1 million atoms of silicon, only one phosphorus atom is added. But still this Nd, although it is much less than the atomic concentration, but this Nd is much greater than Ni, because Nd is of the order of 10 raised to 16, whereas Ni is of the order of 10 raised to 10. And each of this Nd will result in one electron. So how many electrons this Nd will donate per centimeter cube? 10 raised to 16. And how many were there previously? 10 raised to 10. So how many electrons should be there now? 10 raised to 10 plus 10 raised to 16. So we know that 10 raised to 10 is much smaller than 10 raised to 16. So we can say that the number of electrons will almost be equal to how much? Nd. But wait, we said that some of those electrons have now combined with the holes, and so the number of electrons should be less now. So how much exactly? So what I have here is this. Yeah. Now let's say after the holes are destroyed, when the electrons go into them, after some of the holes are destroyed, number of holes remaining per centimeter cube is Nh. So how many electrons should be there? Where for each hole there should be one electron. Obviously one hole will be created when the electron has gone out. So each of the hole will result in one electron. But not only the electrons are there due to the hole creation, but electrons are also there due to the donation by the impurities. So the total number of electrons per unit volume is number of holes per unit volume plus number of donor impurity per unit volume. But we know that now still the product is this, the product of Ne and Nh. So we can write this Ne as this, which is equal to Nh plus Nd, and Nh is Nh. So what we got is a quadratic in Nh. Now, can we assume safely that Nd will be much greater than Nh? So let's try to understand this. Nd was much greater than Ni because Nd was roughly of the order of 10 raised to 16, whereas the intrinsic carrier concentration was of the order of 10 raised to 10. That means before adding impurity, 10 raised to 10 holes were there and 10 raised to 10 electrons were there per unit volume before impurity were added. Now we know that after adding impurity, some of the electrons combined with the holes, so holes number is decreased, so hole number is now less than Ni. And since the whole number is less than Ni, Nh is less than Ni. but Nd is much greater than Ni, and Nh is less than Ni, so Nd should also be much greater than Nh. And since this Nd is much greater than Nh, their sum will be nearly equal to Nh only. Nd only. So, and now that we substitute this entire thing with Nd only, we get Nd into Nh. Nd into this will become Nd, and this will become Nh is equal to Ni square. So Nh is equal to Ni square by Nd. That will be more clear with some one example here. So let's say this is an example. At a particular temperature, the number of electrons and holes per unit volume in pure semiconductor was between the intrinsic carrier concentration was 6 into 10 is to 10. And how many donor impurity atoms we have added per centimeter cube? This many. Now this many donor impurity atoms per unit volume will also donate 1 electron each. So this is the number of electrons that we have got per unit volume. Okay. Now we know that number of electrons will be equal to the number of holes plus Nd. But we know that this is negligible, and so Ne is nearly equal to Nd. So how many electrons are there? The number of electrons is, what is Nd? This. Let's calculate the number of holes. So number of electrons, if we substitute it here, and Ni is 6 into 10 is to 10, so square of that, so 36. So what we will get is Nh, and this Nh will come out to be somewhere around this. And so we say that the number of holes had decreased a lot, and number of electrons have increased a lot, and their product is still Ni square. Now, instead of solving the quadratic, we did the assumption. But what if we don't want to do the approximation and want to solve the quadratic? So let's see. We know that the number of electrons is equal to number of holes plus what is furnished by the donor impurity atoms, and also we know that Ne into Nh is equal to Ni square. So we have got two equations, two unknowns. The two unknowns are Ne and Nh, and the two equations are like this. So let's substitute the Ne as this. Nd plus Nh into Nh is equal to Ni square. So we got a quadratic like this. So if we substitute the value of Nd, we will get this. So how much is this? This will again come out to be what we just now calculated using the approximation. Another way of doing the same approximation is this. So if you remember the quadratic, so this is a quadratic equation. Yeah, it's coming in frame now. Okay. So that is after solving the quadratic. Yeah. So what we are going to do is take a Nd out, and then it becomes like this. And now we do the binomial approximation. So this half comes in. Obviously this is very less. So again what do we get is the same thing. So Nh is equal to Ni square by Nd. So finally what is the conclusion? The conclusion is that the number of holes is decreased because of more recombinations, and the number of electrons has increased to a very large value. Number of holes have decreased to some very low value. Their product remains same. Since the number of electrons that are available for conduction are much larger, we say that the majority charge carriers in n-type semiconductors are electrons, whereas the minority charge carriers are holes. Now coming to this p-type semiconductors, let's discuss about them. So I hope everything is going fine only. So moving on to those p-type semiconductors. P-type. So what happens in p-type is we add what are called as acceptor impurities. Or acceptor impurities are also the trivalent impurities because they have got 3 electrons in the last shell. Trivalent impurities. Again, when we dope this pure silicon semiconductor with those trivalent impurities, what we get is called as a p-type extrinsic semiconductor. So intrinsic means pure and extrinsic means impure or doped. DOPED, extrinsic, EXTRINS, okay, extrinsic semiconductors. So some of those trivalent impurities are generally like boron, and yeah, so boron generally only is preferred. So some of those silicon atoms place will be taken by this boron. So obviously it has got only 3 electrons, and these 3 electrons will be able to form the bond with those 3 silicon atoms, but here the bonding is not there. Obviously other bonds are also there. If you want, we can show these bonds like this. So since this silicon atom here, it's not able to form the bond with the electron here, so what we say is that there is a vacancy here, and so upon the addition of each acceptor impurity or each trivalent impurity, a hole is created, a vacancy is created. And so when we apply the electric field, obviously those electrons will be able to conduct electricity in the valence band. And so in this case, what happens is the number of holes increases. And since the number of holes increases, most of the conduction is done by these holes, and the number of electrons decreases. And even in this case of p-type semiconductor, again Na into Nh is equal to Ni square. Now we know that this number of holes have increased. Each boron atom gives one hole, so lots and lots of holes. Now what happens to the number of electrons? This number of electrons decreases. Why? Because we know that those free electrons, they are hovering all around the nucleus, they are hovering all around the entire silicon crystal, and while traveling and moving randomly, the probability that they encounter the holes and combine with them is large. That's because more and more number of holes are available, so more probability that they will go into those more number of holes present. And so this Ne decreases. So Ne decreases because of electrons recombination with holes, and holes increases because of more supply by boron atoms, but their product remains same. So in case of p-type semiconductors, the majority of the current is through the hole current. So hole current versus electron current. So IH is much greater than IE in case of p-type, and then IE is much greater than IH in case of n-type. So that was about the extrinsic semiconductors. Alright, so let's move ahead now. Now we come to the p-n junction. Okay, what if we combine those two kinds of semiconductors, those two kinds of extrinsic semiconductors? So what we get is something called a p-n junction. So this is half of the silicon crystal, and this is half of the silicon crystal. In this half of the silicon crystal, what we do is we add lots and lots of boron, which is the trivalent impurity, which gives lots and lots of holes. So lots and lots of holes are there, lots and lots of holes. And then there are here lots and lots of electrons. Why? Because we have doped them with phosphorus. So phosphorus here, and here this is boron. So this region becomes the p-type, and this what region becomes is called the n-type. Now what starts is something called a diffusion process. Let's understand the diffusion process in a bit of detail. Now diffusion happens because of two things. Two things are required. First necessity of diffusion is random motion. Random motion. A second requirement of diffusion process is the concentration gradient. We all know that when we have, let's say, a box in which there are two compartments, and here there is a let's say oxygen gas at a high pressure, and lots of gas molecules are there and they all are moving rapidly, isn't it? So let's say this is having the temperature T and the pressure is P, and we know that PV is equal to nRT. Now let's say this is compartment 1 which has got temperature T, but the number of moles is N1, and that's why the pressure is V1. We are assuming same volume here, and here in this case again we have oxygen again at the same temperature T, but the number of moles is N2, which is quite less. And so if we see this PV equal to nRT, PV equal to nRT here, so temperature being same and the volume is same because two compartments, same volume, so this is P2. What happens when we remove this partition? This partition is broken down. Obviously you all will agree that these some gases will go from here to here. Now what is the reason? What is the reason? Why will they go there? Why not these atoms or these molecules of oxygen here? They come here. So what happens is, let's understand. What happens is actually random motion. So let's consider the x direction of motion only. Obviously there are y component of motions and z component of motions also out of the plane. We are not concerned with them. Let's consider the area A. And let's define something called n here. Well, we already have n. Let's say this n is the number of molecules per unit volume. Alright, and since we are considering the random motion, so, and let's say this area of cross section is A, and all of these electrons, all of these molecules on an average they move with the root mean square velocity. That is what we can say, and that root mean square velocity VRMS can be written as root over 3 RT by m. So these will have their velocity. So let's say because of the random motion, half of these molecules have velocity like this and half of the molecules have velocity like this. So that is this Vx here and this is a Vx here. Obviously they may have some Vx, Vy and Vz also. Now let's consider this length V, which is Vx dt. Alright. Now in dt time, what is the distance covered by each molecule in x direction? Distance covered will be equal to their velocity into time. Now there are molecules all over here. We are interested in finding out how many molecules will be crossing actually this cross section, this one. Alright. Now let's consider this molecule. This molecule in dt time will cover Vx dt distance, and if it's moving like this, then it will cover Vx dt, but then this entire thing is Vx dt, so it is at a distance of less than Vx dt from this, and so it will be able to cross. But if we take this molecule here, in dt time how much it will travel? Again it will travel Vx dt, but then its distance from this red cross section is more than Vx dt because it is outside this cylindrical volume, and so this molecule after traveling Vx dt distance in dt time won't be able to cross from here to here because that is larger than Vx dt. So what can we say? Which all molecules will be able to cross this red cross section in dt time? Whichever are at a distance lesser than or equal to Vx dt, isn't it? So can we say all of these molecules? Well, half of these molecules are moving in opposite direction, so they won't be crossing. So we can roughly say that half of the molecules will be. Alright? Okay. So, how many molecules will be there in this? So the volume, is AVX dt, this is the volume, into the number of molecules per unit volume. These many molecules and then divided by 2. These many molecules will be crossing this cross section A in dt time. So what about per unit time? Per unit time t. So what do we get is NAVX by 2. This is the number of molecules that will cross the red cross section per unit time. Alright. Now what is it proportional to? It is proportional to how many are present per unit volume. Now let's consider the other compartment here. And again do the same thing. Again take this Vx dt. Again the same. Now we have taken, if you remember, same temperature. Here also. And since the temperature is same, the velocity is same. So the velocity with which these are moving at the same rate, these at the same velocity, these are also. So that's why we have taken the same Vx. Alright. Now, how many molecules will be crossing again this red cross section like this? Now here the number of molecules per unit volume is different. So if we consider the previous one to be N1, now the number of molecules that will be crossing like this will be equal to N2, because the number of molecules per unit volume here is different. So what we understood, here in the left side we have got huge number of molecules per unit volume. Huge number here. And how many molecules are going in this direction due to their random motion? N1A Vx by 2. And on the right compartment we have got fewer number of molecules per unit volume. And how many of them are going in this direction? N2A Vx by 2. So what is the overall net transfer? Obviously more are going from here to here because N1 is more, and less are going from here to here because N2 is less. So there is an overall shift in the molecules from this side to this side. This is called diffusion. And why this diffusion is coming? Is it because these are moving more faster than these? No. Both have got the same velocity. Both have got the same area of cross section to transfer. But simply that the number of molecules here are much more than the number of molecules here. So this diffusion is something which is like the transportation from high concentration to low concentration. And remember what is required? Random motion. So with the help of this random motion there will be a net flux of molecules from one side to another side, and that will be equal to this rate. Alright, so now that we have understood the diffusion process, we can go back to this PN junction. Hopefully you don't have any question in this area. Even if you have some doubts, you can please do ask in the WhatsApp group, and I will try to give the best explanation possible. Alright, so now that we have understood the diffusion that takes place because of the concentration gradient, now let's come back to the PN junction. Okay, let me just take another page here. Okay. As we can see here that there are lots and lots of high concentration of electrons in the conduction band in those n-type, and those electrons are able to come go anywhere around the crystal structure. So these electrons, which are all free to move in the conduction band, they can go anywhere. Obviously they are more in number on the left side, which is on the n side, and those free electrons in the p side are very less in number. And so that diffusion will start of those free electrons here in this region. Now as these electrons which are diffusing from the n-type to p-type, these free electrons, they will come into the region of huge number of holes, and this huge number of electrons are diffusing into the huge number of holes. Obviously these electrons are going to combine with these holes. Now as soon as these electrons combine with the holes, what happens? They combine with the holes. So if you remember why the hole was there, first of all, that was because of the boron. So if we draw this this is the silicon. So one here, and one here, but there was a vacancy here. Now this electron are coming from this n type into the hole of the this was the hole created by boron, and the electron from the n type has come here and sit here. So this hole is gone, and as soon as this hole is gone, we know that this boron has got an additional electron, and since the boron has got an additional electron, it will be negatively charged. So lots and lots of electrons are going to come here and combine with the holes, and what it will create is a region in which there are lots and lots of negative boron ions. Okay, so but what will happen to the n region? From the n region, the electrons are gone. Now in the n region, what we have? Let's say this is the mesh. So we are trying to draw some kind of a 3D representation like this. So this is the silicon mesh, and this is the silicon mesh here, and this is the p type, and this is the n type. In the silicon mesh, somewhere what we have is phosphorus. Phosphorus is able to combine with the 4 atoms of silicon. 1 electron is still remaining, and this electron is in the conduction band here, and all of these phosphorus are given those electrons. Now when we have this n type only semiconductor, we know that once the electron leaves those phosphorus will become positively charged. So shouldn't this n type semiconductor, because of this phosphorus, let's call it pH, because of this phosphorus, shouldn't it become positively charged because phosphorus has lost the electron? Well, overall it will be neutral, isn't it? Why? Because the electron which is given by the phosphorus is within the crystal lattice only. Obviously it is roaming here and there, but the electron is still there. But when we combine this n type with the p type, those electrons which were hovering all around the phosphorus, they have gone now to the p region, and once these electrons have gone, what is left here is the positively charged phosphorus. So what are we going to get is, because of the electrons diffusion here, we will get a region in which lots of phosphorus will be positively charged. Let's call it donor impurity positive. Let's call it DD only, or ND we can also call it. So there are lots of positive charges here because the electrons of the phosphorus have gone. And where have they gone? They have gone into these borons, and all of these borons are all negatively charged. Now, what about here? The free electrons are gone now. Who will conduct electricity? No one. Okay, then what about here? Well, previously there were lots and lots of holes here. See, lots and lots of holes. But now all of these holes are filled up by electrons. So holes are gone. So charge carriers are gone. So who will conduct electricity here again? Who will conduct electricity here? No one. Because all the holes are filled up. So in this region, the charge carriers are gone. Electrons gone from here to here, combined with the holes. Holes also gone, electrons also gone. So this region is depleted of the charge carriers, and this region is called the depletion region. Depletion region. Okay, so moving ahead. Now this depletion region is found, alright, but up till what it extends and when does it stop? And why should this formation of depletion region stop after a while? That is because as soon as the electrons start to jump from the n type to p type because of diffusion, a reverse phenomena starts, and this reverse phenomena is called drift. Now drift you have learned very well in current electricity. It's a very simple phenomena. What is this drift actually? So let's say if we have a conductor and which has got lots and lots of free electrons, if we apply an electric field, what happens? All of these electrons start to move. When these electrons start to move opposite to electric field, we say that they are drifting. So drifting is a phenomena in which the charge carriers are moving not because of their concentration gradient, but because of the external force applied by the external electric field. So that is drift. So alright, so I hope you understand the diffusion. See, diffusion also results in current flow, because ultimately what is happening, electrons are going from here to here, isn't it? So electrons are flowing means what? Current is flowing. So current is flowing because of what? Diffusion. Why? High concentration to low concentration. So this is one kind of current, diffusion current. And then there is another type of current which flows in the whenever there is an electric field, and this is called the drift current. So drift versus diffusion, remember the difference. Okay, moving ahead now. Yeah. So we were discussing that in this junction, this is called the p-n junction. Junction means the boundary between the p type and the n type. So we were discussing that the electrons here will jump here, and positive charge will be created. Let's say the electrons have just now started to jump from what? From n type to p type. So the number of charge carriers, the number of phosphorus positive charge is less right now. So let's say we have one phosphorus, and we have another phosphorus, and we have another phosphorus. The process of diffusion from n type to p type has just started. So not many electrons have gone here. So the number of positive charges also are very few in number. And what about this boron? Since the few electrons have started to come onto the p side, so boron negatives are also less in number. Now what happens is, because of this charges, there is electric field created from this positive charge to negative charge, like this. Now what will this electric field try to do? Let's check the direction of force it will apply on an electron. So we know that the electron gets a force opposite to the field. So if the field is like this, then the force on the electron is like this. So this is the direction of force that the electron is going to get. Now, so as soon as the electron will come here, like this, to the left, because of diffusion, isn't it? From is the video coming properly, or is it too dark now? I think something has happened here. Maybe it's the so charging is 5% left. So once just give me a moment, I will put my mobile in charging mode. Only 5% of the battery is remaining. So let me just put this charging right. Yeah. And tap to focus. I hope it's fine now. Alright, so yeah, sorry for the disturbance. Moving ahead now. So as we were discussing, this electron would like to diffuse here, but this electric field which has generated, obviously if the electron leaves here positive charge, electron goes here negative charge, so already lots and lots of negative charge, lots and lots of positive charge. So positive and negative will produce electric field towards left, and this electric field will produce a force on the electron towards right. So we know that because of this force, what will happen? Well, the electrons will start to move in opposite direction. So we can say that there are now two different processes. Actually, they are counter processes. They are taking place. Electron would like to diffuse here towards the left because of concentration gradient, but then electrons will get a force in opposite direction, and because of that force, the forceful motion, they will start drifting towards the n-type region. But initially, when the diffusion has just started, very few electrons have diffused here, and so very few positive charge and few negative charge. And since very few positive and few negative, the electric field is less. And if the electric field is less, this force is less. And if the force is less, the drift is less. So drift is small, and diffusion is large. So more are diffusing towards left and less are drifting towards right because of the force. But as more and more diffuse, this positive charge keeps increasing. And since more and more are diffusing, the negative charge here increasing. So both the positive charge here increasing and the negative charge here also increasing because of more diffusion, and because of which this electric field here, it keeps increasing in magnitude. And if the electric field keeps increasing in magnitude, then the force which makes it go back, the drift force, the drift keeps increasing until a time comes when so many electrons have diffused, because of which such a strong electric field is produced, and because of this strong electric field, even the drift has also increased to a good level. A time comes when the number of electrons diffusing because of concentration gradient towards left becomes exactly equal to the number of electrons which are drifting towards right because of the electric field. And we say that this is something like a steady state. So number of electrons coming towards left is equal to number of electrons coming towards right. So there is no net motion, isn't it? And now that there is no net motion, whatever electrons have come here, that's all fine, and whatever electrons have left here, that's all fine. So what we have created in a steady state or in equilibrium is a region of negative charges here of boron and positive charges here of phosphorus. Both of these can't create or can't conduct electricity. Why? Because phosphorus, this positive charge, can this phosphorus move? Isn't it? No. Why? Because they are bound. Phosphorus can't move. What about the negative charges here? Can these negative charges move? No. Why? Because these negative charges are blocked into those holes. So neither the negative charge moves nor the positive charge moves. So this region is actually depleted of the actual charge carriers, and whatever these charges are here, they just remain at their places. This is also called, that's why, space charge region. A space charge region. So what is a space charge region? A space charge is a region in which the positive and negative charge space charges are created, which is also the depletion region. Now this remember that the diffusion and drift, it happens actually near the junction here, near the junction, and there is something called the width of depletion region, this one. Let's represent it by W. Now this width of the depletion region is quite small actually as compared to the total length here, length. So this is the p type, this is n type. Okay. This is also called the dynamic equilibrium. Why it is called dynamic steady state or equilibrium? It's not that the drift has also gone, stopped, and drift has also stopped and diffusion has also stopped. It's not like that. Drift is also occurring because of concentration gradient. Diffusion is also happening because of concentration gradient, and the drift is also happening because of the electric field. But both are cancelling each other. So that's why a dynamic equilibrium, not a static equilibrium in which both have stopped. It's not like both have stopped here. Okay. Now let's consider this depletion region, which is depleted of the charge carriers. Where do you think here in the entire region the electric field will be maximum? So we are going to consider point A, point B, and point C. Now let's consider the electric field at A, B, and C. At A, in which direction these positive charges will create electric field? These positive charges will create electric field like this, isn't it? What about the negative charges? Well, negative charges can be divided into two categories, these negative charges and these negative charges. So at A, the electric field created by these negative charges will be like this. It will be towards them, isn't it? But these negative charges will create electric field like this towards them. So we can say that the negative charges electric field is somewhat getting cancelled out. So what remains is roughly the electric field of positive charges. Then what about here? Well, the positive charges, these positive charges will create electric field like this, and these positive charges will create electric field like this. Again, the electric field of the positive are somewhat cancelled out. So what remains is the electric field here of the negative charges. And how are these negative charges creating electric field at this point? the attractive one. So like this. So this electric field is there, this electric field is there, but not very much, because some of the electric fields are cancelled out. But let's consider B. At B, all of these positive charges will be creating electric field like this, because obviously positive charges repel. So this electric. But what about all the negative charges? Well, all the negative charges are also going to attract here. All these negative charges. So we can say that exactly at the junction boundary, the electric field is maximum. So actually, if we plot the electric field versus x graph, so here, so this is the depletion region, and this is E versus X. This is the junction boundary. This is the P type here. Let me just draw the P type. This is all P type. This is the junction boundary, and the remaining, which is not shaded, is the N type. And this is the depletion region, and there are lots of negative charges here on the P side, and there are all the positive charges on the N side. So how is the electric field? Well, first of all, we can say that the electric field is in this direction everywhere, and the electric field is maximum here at the junction boundary. So this backward electric field can be drawn as a negative, isn't it? Generally we take the positive x direction to be the positive direction electric field. So I will draw the graph below the x-axis, because the electric field is considered to be negative because it's in the this backward direction, and obviously it is maximum at the junction. So it will be something like this. Okay, now what about exactly at the end of the depletion region here? Well, exactly at the end of the depletion region, you can understand that the net electric field will be some kind of a zero value. If we consider them as the sheet of charges, because the width is very small as compared to the cross section area. So this area of cross section is A, and these transverse dimensions are much longer than this width of the depletion regions, and that's why we can consider them as the sheet of charges. So if we keep if we check the electric field here at the junction boundary, all of these negative charges will create attractive electric field towards them, and all of these positive charges will create a repelling electric field away from them, and so the net electric field here will become zero. So that's why. So we know that the electric field will be always within the depletion region from the N type to P type like this, and because of which there will be a potential difference. So obviously along the electric field the potential decreases. So this is the high potential region, and this is the low potential, V low. And this potential difference across the ends of the depletion region, this is called the barrier potential. Barrier potential. So barrier potential is V high minus V low. What is V high? V high is the potential at the end of the depletion region on the N side, and V low is the potential at the end of the depletion region on the P side. So this is what is there for the p-n junction in equilibrium. Okay, I can see the question of Avinash Shankar. He is asking whether the equilibrium will be dynamic or static. So the equilibrium is actually dynamic. Okay, is the audio and video clear? I guess it's all fine only, right? Okay. So everything is very nicely explained actually in the NCERT textbook. So today I will be giving you a reading homework. You have to understand all this p-n junction formation and everything in the semiconductor chapter of NCERT textbook. So let me just open it. So today you will have a homework to read up to page number 479. So the homework is from up to page number 479, and right from page number 467. So you go through this and you tell me if there is any doubt in understanding whatever we have discussed so far regarding the extrinsic semiconductors, intrinsic semiconductors, and the p-n junction formation, and also the barrier potential. Now, what happens to this p-n junction when we connect it to a battery? Well, that depends on how we connect a battery. So battery can be connected in two ways. If the positive terminal of the battery is connected to p type and negative terminal of the battery is connected to n type, we say that the p-n junction is under the forward biased, vice versa. Sometimes the question comes on how the barrier potential varies with the x. So if you want to plot the potential, so keeping the low potential as 0, so this is potential versus x. Now since the electric field is somewhat linear, the potential variation comes out to be parabolic, isn't it? Because potential is integral of electric field, so integration of linear will be parabolic. So we'll start from 0 potential on the lower side, so which is V lower, and parabolic here like this, and then again like this, the other parabola, and this will be V low, V high, and this will be V low, and again the constant. So constant potential difference here in this region. This is the no electric field region here. So no electric field here means no potential change. So all potential constant. All of these are in high potential, whereas all of these are in low potential here. All of these are all the low potential regions, and the variation of potential from high to low or from low to high is like this. So this is parabola number 1 up till here for one straight line of electric field, and then there is another one. So like this. I remember once in mains a question was exactly at where the electric field is maximum. The answer was at the junction. So that's why we discussed this. Okay, now coming to the p-n junction and the forward bias. Okay, what we'll do is we'll continue in the next class. So in the next class we'll discuss the p-n junction under forward bias and reverse bias, and the working of a diode. I mean, allowing the current to flow in one direction and not allowing the current to flow in opposite direction. Why does it happen? Okay, so thank you very much for this 1 hour time you have given, and sorry for the first 10 minutes in which nothing happened actually because of the problem in the alignment. So I will be better prepared from next time onwards, and if you have any questions you can always ask in WhatsApp. So thank you. So I am stopping here right now the live streaming. Bye bye.